Hi everyone. Let's find out why finding areas of regions under graphs of functions can be useful. In the first exercise, we were given the velocity of a runner at specific times, and we must determine the distance traveled by the runner during the first 20 seconds using any method we wish. If you would like to try this exercise on your own, stop the video now. You can also download these notes using the link in the video description. The velocity at the beginning of the trip was 1. At the end, it was 11. This suggests that the velocity was increasing over time. At the beginning, the velocity was 1. At the 5th second, the velocity was 2. What was the velocity between 0 and 5? We don't know. We don't know that data. Most likely, the velocity was somewhere in between 1 and 2. Because I'm allowed to use any method I wish to estimate the distance traveled, I will assume that during the first 5 seconds, the runner was going with the speed given at the beginning of the time interval, which means that during the first 5 seconds, the runner ran 5 times 1. The velocity was 1, and the time spent running with that velocity was 5, which means that the distance during the first 5 seconds was 5. I will do the same thing for the next time interval. I will assume that during the next 5 seconds, the runner was traveling at the speed of 2, the beginning speed. That gives me that the distance ran was 5 times 2, velocity times time. In the next 5 seconds, I will assume that the runner ran with a velocity of 4, and I will get 5 times 4. Finally, I will get 5 times 7. When I compute these numbers, I will get 5 plus 10 plus 20 plus 35. When I add these numbers, I will get 70. This tells me that the approximate distance was 70 feet. I know that this answer is an underestimate because during the first 5 seconds, I took the lower velocity to estimate the distance. During the next 5 seconds, I also used the lower velocity instead of using the higher velocity. Most likely, during these 5 seconds, the runner was going slightly faster than 2 and probably less than 4. That velocity changed over time, but most likely during those 5 seconds, the velocity was somewhere in between 2 and 4. But I assumed that it was 2, and that is why I got an underestimate. To improve this estimate, I wish I had data every 1 second. If I had data every 1 second, my approximation would be much better. Let's see if we can complete a similar exercise, this time not with velocity and distance, but with the rate at which air is blown into a balloon and the total amount of air blown into a balloon. If you would like to try this exercise on your own, stop the video now. I will assume the same method. So I will also use the beginning rate during each time interval. Because I'm assuming that during the first 5 seconds, the rate at which air was blown into the balloon was 10, during the first 5 seconds, the amount of air that got into the balloon was 5 times 10. Then, during the next 5 seconds, I will assume that the air was going inside of the balloon at the rate of 9, and I will get 5 times 9. Then I will get 5 times 5 and 5 times 2. These are the remaining beginning rates at each following interval. When I compute these numbers, I will get 50 plus 45 plus 25 plus 10. When I add these, 45 plus 25 is 70, plus 50, that's 120, plus 10, that's 130. The units are centimeters cubed. This time, I get an overestimate because the beginning rates are higher than the ending rates on each interval. If I had data for every second, again, my estimation would be better. What do these computations have to do with areas of regions under graphs of functions? To show you the connection, I plotted these points and these points on 2 separate graphs. The first graph shows the data from the first table, the second graph shows the data from the second table. These are the 5 data points. When I connect these dots, I get a guessed graph of the velocity function. If someone asked you to compute the area of the region under the graph of this function, you could use the left endpoint method. And if you did, you would get the following rectangles. These rectangles, or rather the areas of these rectangles, would approximate the area of the region under the graph of this function. Note that the areas of these rectangles are exactly same as the computations we did when we computed the total distance traveled. It was 5 times the first velocity, 5 times the second velocity, 5 times the third velocity given in the table. This suggests that the area under the graph of the velocity function gives you the total distance traveled. Or, to say it differently, velocity is the rate of change of position, and the area under the graph of the rate of change of position gives you the total change in position. In the second problem, these are the data points. If I connect them, this is what I get. When I use the left endpoint approximation to approximate the area of the region under this graph, these are the rectangles I get. These rectangles have areas exactly 50, 45, 25, and 10. This suggests again that the area under the rate of change of the air inside of the balloon is exactly the total change of air in the balloon. One more time. This was the rate at which position was changing. The area underneath was the total change in position. This was the rate at which the air in the balloon was changing. The area underneath is the total change of the air in the balloon. This is a general rule. Before I can fully state it, we need to make one more observation. We are given a rate of a population growth of a small village, and we must determine if the population in 2025 was greater or less than in 2020, by how much? In other words, we need to know the net change, where the word net means total, in population between 2020 and 2025. According to the graph, the rate at which the population grew was 15 during the first 3 years, which means first year, 15 more people showed up. Second year, 15. Third year, 15. Altogether, during the first 3 years, 45 more people showed up. Note that that's exactly the same as the area of the region under the first piece of the graph. Between 2023 and 2024, the rate was negative 15, means that during that year, 15 people left. This is the same thing as the area of this second region. During the last year, only 10 people left, and that is because the rate was negative 10. Which means during the first 5 years, 45 people showed up, 25 people left. 45 minus 25 is 20. That means that the population in 2025 was greater by 20 people. Note that the areas under the graph of the function that were above the x-axis were taken positively. Areas below the x-axis were taken negatively. Whenever you're given a rate, the area underneath gives you the total change, and that total change is positive if it's above the x-axis, and it's negative if it's below the x-axis. This is exactly the statement of the net change theorem. If you're given some q prime, where q prime represents the rate of change of some quantity, then the net change of q from A to B is the signed area between the graph of q prime and the x-axis. And the word signed means it can have a positive sign or negative sign, meaning if it's above the x-axis, it has a positive sign. If it's below the x-axis, it has a negative sign, and we subtract it. Let's see if we understand this theorem by completing one more problem. This time, we're given the rate of change of the temperature in Fahrenheit per hour in an office building. We must compute the net change in the building's temperature during the 12 hours shown on the graph. If you would like to try this problem on your own, stop the video now. Remember what the theorem says. When you're given the rate of change of something, the signed area underneath gives you the total change of that something. We are given the rate of change of the temperature. The area will give us the total change in the temperature, as long as we remember to take the areas above the x-axis positively and the areas below the x-axis negatively. Which means all I have to do is compute this area, and subtract the two values. To compute the area above, I will split this region into some geometrical figures. I see I can split it into this rectangle. I know that this rectangle has length 7, height 1. This area is 7. The area of this triangle is 1/2. The area of this triangle is 1/2. And the area of this triangle is 1/2. Let me write everywhere. 1/2, 1/2, and 1/2. Finally, the area of this remaining square is 1. Altogether, the green area is 7 plus 1 plus 1, that's 9, plus half, that's 9.5. The area below the x-axis is this area, which is 3, and the area of the triangle, which is 3 times 3 times 1/2, which is 4.5. Altogether, the red area is 7.5. When I subtract the green area from the red area, I will get 2, which means that the total change in temperature over the first 12 hours was 2.